The integration of exponential functions is one of the simplest concepts if we focus on a few details. First, what is an exponential function? In an exponential function, we have a number as a base, and the variable is in the exponent, whether it's x or t or any other variable. But what makes it an exponential function is that the variable is in the exponent, not in the base. We have conditions on the base that it be a positive number greater than 0 and not equal to 1. Because if it were 1, no matter what power we raise it to, it will stay 1. 1 to the power of any number equals 1. So we won't have an exponential function. For example, we have 8 to the power of x, an exponential function, 2 to the power of x, an exponential function, e, the special number, to the power of x, a special exponential function, and e equals 2.71. Let's go to the fundamental rule we're learning today, the integration of the exponential function. This exponential function, a to the power of x, we take the function as it is and divide by ln of the base, which is the constant number here. ln of the base we can get with the calculator, and we say plus the constant c. If the base is the special number e and we apply the same rule, we take the function as it is here and divide by ln of the base e plus the constant c ln of e will equal 1. So we get the same function, e to the power of x comes out here plus the constant c. So this means the integral of the function e to the power of x is itself e to the power of x. And this is one of the wonders of the special number e. When we look at the graph of the exponential function, we want to focus on the constant, or the base here, the exponent stays as x. We want to see what happens when we change the base. If we decrease the base, the function will keep going down, or its acceleration decreases. The more we increase the base, the more the function's acceleration increases. And we have the special acceleration when the base is e. This is the acceleration that always comes out in processes of growth and decay in nature. Now we want to move to the curve, or the area under the function's curve. What we want to notice here is that if we move 1 unit from 0 to 1, we have an area here, but the area from 1 to 2 is much larger than the 1 here. Every step we move, an area comes out much higher than the one before it, meaning we don't have acceleration, or we don't have constant acceleration. The acceleration itself is increasing. And this is an important point in exponential functions. Let's compare some functions. Here we have a constant function, and here it's integral. Here we have a linear function, and here it's integral. And here the exponential function, and here it's integral. We want to compare the areas added under the function's curve between the function's curve and the x-axis. In the constant function, if we move a step, the first square, a second step, the same value we added, the second square, same as the first, and the third step, same thing. That's why its integral, we jump in a constant slope, 2, 2, 2. That's why the integral of the function y equals 2 is 2x. If we go to the function y equals x, at the beginning the area we brought in here is a triangle's area. Then we brought in an area higher than the one before it, and here we brought in an area also higher than the one before it. Each time we bring in an area higher than the one before it, but the increase here is constant. This is what differentiates it from the exponential function. So the increase we have is constant. That's why its integral is a quadratic function. And finally, we saw the exponential function, that the increase is higher, the increase itself is increasing, and this sentence is very important, that the increase coming in with us, or the acceleration, has acceleration in it. Okay, now we want to see solved examples for the exponential function rule. E to the power of x, we saw it. We apply the rule, e to the power of x plus c ln e equals 1. 2 to the power of x. How do we solve it? We take the function as it is and say ln of the base 2. And we say plus the constant c, 5 to the power of x, same thing, function as it is, ln of the base 5 plus c, 10 to the power of x. Same method. Even 1/2 to the power of x, we take it as it is, ln of 1/2 plus the constant c. A final point. If we have the exponent x but with a coefficient, this being a number like 2x, 3x, 4x, same method, we don't change anything, but we take the coefficient and put it in the denominator. This is the important change. So e to the power of 2x, we take the function as it is and divide by the coefficient 2 times ln e, which equals 1, so we don't put it. Here, 2 to the power of 3x, we take the function as it is here and divide by ln2, the base, and multiply by the 3, the coefficient of x. Same thing, if it's negative 1 here, same method here, it becomes negative. We take the function as it is here, divide by ln of the base 5. 10 to the power of 2x, same method, 10 2x here, here 2 ln 10. Very important that here we have 2x and not x squared or x cubed. X must be of the first degree. And this is the final point we want to pay attention to in this lesson.